So at the end of the last video, we took a look at this concept of what we call the central limit theorem, which gave us this a broad overview of this sampling distribution of x bar and what was true about it. Now this box is not going to be anything that you have to have memorized, because actually it's all been summarized for us perfectly inside of our formula sheet here in our fourth column. Notice that if x bar is a random variable, it can take on random values determined by chance, then we can say that it will have a normal distribution as long as one of the two checks is actually going to be passed. N, the number of items that I'm sampling in order to calculate an average width, is 30 or more, or X, that is the distribution from column 3, has a normal distribution. So this brings up a good time to try to distinguish the differences between columns 3 and column 4. In column 3, we were dealing with things like single items. So we were asking things like, how long is the lifetime of a light bulb? What is a student's score on an exam? Something like that. Whereas over here, we're looking at an average of a sample. So here I might say I want an average test score for 30 people in the class. Here I want a student's test score from the class. So there's a difference between dealing with a single item and an average of items. And that's really the goal here. So I'll know that my x bar, my average of a sample of items, will have a normal distribution if n is greater than or equal to 30, or if the single items had a normal distribution. We also have formulas here with which to calculate the average x bar and the standard deviation of x bar. That is, like, what's the typical x bar and how far away from typical is it common to go. So notice that these formulas require that I know something about the previous column. If I know the value over here, I can say that the average on this side is going to be the same. And if I know the standard deviation from over here, I can say that I can divide that by square root of n, which is my sample size, to get that. Now, since I'm dealing with a normal distribution, we'll see that my calculator commands are still going to be that normal CDF and my inverse normal. Normal CDF will calculate a probability, just like it always does, and my inverse normal now will not just compute a value of x, but a value of x bar. So we're going to try to see how this works as we switch back to example number 2. Let's take a look at this example and try to work through it. A study was made of seatbelt use among children who were involved in car crashes that caused them to be hospitalized. Okay, so this isn't a very fun example. It was found that children not wearing any restraints had hospital stays with a mean of 7.37 days and a standard deviation of 0.79 days. Okay, so I've left some space here because I want to start working down that formula sheet. The first thing I want to do is to see what variable I'm really being given here. What's the random variable? What distribution does it have? Well, notice that I'm being told about how long a child is staying at the hospital. There's an average stay, and there's a standard deviation of stays. But again, that's for a child. So I can see here that I'm working in this middle column, at least right now. So I can say, how about we let x represent the length of stay for a child at the hospital. Okay, this is what I'm working with. And I know that, I guess I'm not really told anything about what distribution I have. I can't really say that it's a normal distribution because the problem doesn't say that, and I don't have any raw data. So here's the best that I can do. I'll say x has an unknown distribution. Now that's okay. I can still tell, though, that I'm dealing with a distribution that, regardless of whatever its shape is, the average length of stay is 7.37, and the standard deviation for the length of stay is 0.79. Well, now let's take a look at part A. This is kind of strange because I don't really know what column I'm in yet. I might be close to column 3, but I haven't been told enough information yet. I don't know my distribution type. Take a look, though. Part A is going to come in and save the day. If we believe that the population is normally distributed. Oh, perfect. Oh wait, we're only going to assume that for this part. But if I assume the population is normally distributed, then the problem says so, and I can confirm that I'm in this third column. And I've already done the first four boxes in here. And so now I could ask, what is the probability that a randomly selected child, notice this is a child, had a hospital stay of greater than a week? So I'm going to go ahead and I'm going to draw out my pictures in the same way I always do. So I'm going to say I have a nice normal distribution. My standard deviation is 7.37. Or sorry, my mean is 7.37. My standard deviation is 0.79. And I want to be dealing with greater than 1 week stay. Well, keep in mind here, X is being measured in days, so a week would be the same as 7 days. So I'm going to go ahead, I'm going to go right here from 7, and I'm going to shade all the way up into the corner. So I would write this as probability that X is greater than 7. I know I can calculate that with a normal CDF, starting from 7, going to 1E99, and then I would type in my 7.37, 7.37, and my standard deviation of 0.79. So this is actually not anything new. This is a question that we tackled back in Chapter 5. So this is really easy. If I went to the calculator, I typed in all this information into my normal CDF, you could go ahead and confirm that you do get back an answer of 0.6802. So there's nothing new or surprising about this question. We should be able to tackle this no problem. But let's take a look here at Part B. Notice something will change. First off, we're not allowed to know that, or not allowed to assume that the distribution is normal, because that was only for Part A. Now we're back to, I don't know what X has. Let's pretend we don't know. What if it was the case that I took a sample of 40 children at the hospital? I did a sample of 40 kids, and then I asked the question, what is the probability that their average hospital stay is greater than 1 week? Well, notice I'm not asking about a kid anymore, right? I'm not asking about this length of stay for a child. Now I'm dealing with an average hospital stay for 40 kids. So things are very, very different. And in fact, this is exactly the moment when I would know, well, wait a minute, I'm trying to find an average stay for a group of people. That's X bar. So I'm going to have to restart by moving down this column. So let's start by defining what the random variable X bar is in this case, find its distribution, do the checks, and find its important parameters. So I'm going to start with this. I'll say, let X bar represent the average length of stay for 40 children. I don't know what that average is going to be. It could vary. So it's a random variable. I can now go ahead and check what distribution X bar has. And I can see that X bar has a normal distribution because I can think ahead about my checks. I only can state it as a normal distribution if I know n, my sample size, is greater than or equal to 30, or if X has a normal distribution. Notice that right now, I don't know that X has a normal distribution. It's got an unknown distribution. But my n is 40. So here I can say since n is 40, and that's greater than or equal to 30, I can say I have a normal distribution. And I can also see that I can find an average for my X bar and a standard deviation for my X bar. So I could be ready to draw an X bar picture. Well, I'm going to follow the formulas from the formula sheet. The average for X bar should be the same as the average for X. Okay, so here's the average for X. That number up there has got to be the same as the average for X bar. The formula on the formula sheet then says that to find the average for the standard deviation for X bar, you have to take the old standard deviation and divide by the square root of n. So I'm going to take the old standard deviation and divide by the square root of n, which is 40. Now I'm often going to go here, and I'm going to make the important note here that we do not want to round off this value. Okay, I'm going to make that really important right here. Don't round this value off. I'm just going to go ahead and feed this exact value to the calculator when I make my computations. So let's see what we get. I'm going to draw a picture here now of this distribution. Notice though my variable's different. I have x bar. I'm going to put x bars on my number line now. So I want to know, what's my average x bar? Oh, I have that. It's still 7.37. Notice though that my standard deviation is different now. It's now 0.79 divided by square root 40, and I'm not going to round that. I still want to know, what is the chances that someone would be in the, or this average comes out greater than 1 week. So I'm still going 7 days and higher. But in my picture, I'm dealing with this space. So I want the probability that the average is greater than 7. Well, it's still a normal distribution, so I can still use normal CDF. And I'm still going from 7 to 1E99. And my standard, or my mean here is still 7.37, but my standard deviation has changed. So I'm going to have this right here. Now I'm going to go to the calculator and crunch this out to see what I ultimately end up with. So on the calculator, I go ahead and I'm going to click on normal CDF. And again, I'm going to be starting from 7. I'm going to go to 1E99. My average was 7.37, and my standard deviation is a different value here. My standard deviation is going to be 0.79 divided by the square root of 40. So I can go ahead and type all of this in. This is what I end up with. And now when I go ahead and I hit enter, I get a value of 0.9985. So if I go back to my notes, I can go ahead and say that my value here of 0.9985 is the likelihood that my average will be greater than 7. The chances that any one kid had stayed in the hospital for over 7 days, about 68%. But when I start talking about averages, my probabilities can be very different. So hopefully this shows you how things are a little bit different when I start to calculate problems with x bar. I have to make sure that I adjust my standard deviation, do my checks differently, all of this sort of stuff. But that ultimately, I'm still drawing the same picture and using the same sorts of calculator commands. In the next video, we'll take a look at part C down below, which asks a very different style question. And we'll kind of see how to tackle that and start to get into some of our first uses of calculating probabilities to conduct inferences.